Okay, let's start with Riemann sum graphs. So this whole idea is a little bit complicated, so I decided it would be best to instead just give you a bunch of things to memorize in case you don't really want to figure all of this out. So let's start with right Riemann sums. Right Riemann sums are an under approximation of the integral when the function is decreasing. So here's an example of a right Riemann sum graphed out. You can see that it clearly has all these white spaces right here. Right Riemann sums are over approximations of the integral when the function is increasing. So right here you can see that there's that little bit of overlap where it's going over. That's an example of an over approximation. This will go for any kind of graph, whether it's a parabola or x to the power of 3, all that kind of stuff. When it is increasing, or when it is increasing and when it is decreasing, it'll always be that way. Then paralleling with that, left Riemann sums are under approximations of the integral when the function is increasing, right? So as you can see, when this thing is increasing, there's clearly some obvious gaps right here. And then it is an over approximation of the integral when the function is decreasing. So as you can see, as it's going down, there's that little bit of overlap. So these graphs look mostly the same, but there's a very important key difference, which is what side of these rectangles is touching the line. So let me zoom in here. For the right Riemann sums, these two right here, it is the right side of the rectangle that is touching the line right here. See? Right side, right side, right side, right side, right side, right side, right side. And then right here, it's a bit more apparent. Same goes for left Riemann sums, except the reverse. So as you can see, the left touches here, 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 and here. And conversely, left, 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 left. So that's a pretty good way of remembering how it goes. In fact, if you can just draw this graph, all of this from before can be figured out on your own. Now let's go to trapezoidal sums, which are the same thing except it's like a different shape where it's kind of minimizing this thing right here. What's it called? Trapezoidal sums are an under approximation of the integral when the function is concave down, and an over approximation of the integral when the function is concave up, right? So under for down, over for up. That's all you have to remember. You will not have to expect anything about over or under approximations for midpoint Riemann sums, but you will see them in other contexts. We will get to that very soon. So sometimes you will have to construct a Riemann sum on your own, for example, with a table. So here I have the numbers. It might be a little bit hard to see. 0, 3, 316, 526, 630, 836, 1142. So let's look at a right Riemann sum. The right Riemann sum is always going to be touching the right side of the table and missing the last left one right here, as you can see. So everything that is highlighted in green is going to be a right Riemann sum. So for the first one, you have f of 3, this one right here, so 16 times the width of the distance between these two. So 0 and 3, the distance is 3, so it's f of 3, so 16 times 3, which gets you 48. Next will be f of 5. The distance between 3 and 5 is 2, so the width you put here is 2. So f of 5, which is 26, times 2 is 52. So you just keep on doing that, 48, 52, 30, 76, 126, until you reach the end right here, as I've mentioned. F11, 3, right? That width right there is 3 from 8 and 11. That's how you'd go about that. You just add those all up, and you get a number like that. Now, left Riemann sums are like the opposite of that. As you can see, everything highlighted in pink is that, and it hits all of the numbers on the table except for the rightmost one. So you start with 0 instead of 3 this time, and the width between 0 and 3 is once again 3, but instead of finding the y value for 3, you're finding the y value for 0, which is, well, just regular 3. So you have 3 times 3, which is 9. Then you do the same thing for 3, which is now being done with 5. So 3 and 5, that's 2. And then you're finding that y value right here, which is 16. So 16 times 2 is 32. And you keep on doing that once again until you reach x equals 8, right? So f of 8 times 3, because you have 8 and 11 again, right? It's the same thing, except you're just moving that slider 1 to the left. Now, when you have things like midpoint Riemann sums, which is the thing I was going over just a second ago, you're really just going for the ones in the middle. So every other one is the one you're including. So let's take a closer look right here. Right, you have, oh goodness, that's a bit too much. So you have 1, 3, 5, 7, 9, 11, 13. That is 7, so you will always have an every other one. So you can't be an outside one, and it has to be the one next to that outside one. So this won't always work with every single one of these. Specifically, it will only work with odd number tables, right? If you have one that goes one more, then it just won't work. That's why I couldn't do it with the this one right here, because that's 1, 2, 3, 4, 5, 6. Since we're over here, I guess I'll go over trapezoidal sums. So this one is a bit more complicated. You have to find the y value for f of 0 and f of 3, right? 0 and 3. Then you have to cut that in half, and then you have to multiply it by the width between the two. So 3, 16, 19 divided by 2 times 3, and then you do the same for now f of 3 and f of 5. So 16 and 26, add those together, divide that by 2, multiply by 2. So you get, what's that, 30, 40, 42 for that one. Right, so it's basically following that trend. You're just going to keep on going through these until you reach the last one, which will be f of 8 and f of 11 divided by 2 times 3, and you will get 291.5 if you do that one out. So now let's take a look at summation of definite integral notation. So I've went about creating an easy formula for you to follow instead of having to deduce it. This is almost the only way to do this, efficiently. So I'd probably whip out some flashcards for this. Let's start with the very simple plug and play of this. If f of x is equal to x squared minus 1, evaluate k equals 1, fk plus 1. So what it's saying is that you have to find the values of 1 from 1, 2, and 3. So you're just adding 1 each time. So you have the k values of 1, 2, and then 3. You're stopping at 3. Basically, you're always starting at 1, k equals 1, and then you're adding another one, and then you're adding another one, and you're adding another one until you hit this barrier right here at the top, which is, for this one, 3. So you have 1, 2, and 3, and then you put that in. So let's start with k equals 1. You put that in, 1 plus 1 equals 2. You do that for the next one, 3, 4. So now you have your f value. So I have, for the first one, for example, you have f of 2. You put f of 2 into here. 2 squared is 4, minus 1 is 3. That's your answer. Now you go and do this for each one, and then you add them all up together to get something like 26, for example. That would be your answer for this question. That's how you would evaluate that. Now, let's say you're trying to construct one of these. The question might ask you, if 20 subintervals of equal length are used, write a summation that would represent a right Riemann sum approximation of crowbar 7, 2, f of x dx. So first you need to find the width of all your subintervals, and that's going to be the top of your crowbar minus the bottom of your crowbar over your amount of subintervals. So I have 7 minus 2 over 20, and that gets me 1/4. That's what I've highlighted in red if you can't see. Next, you're going to put it into the little formula I have over here, which is the sigma at the top. At the bottom you always have k equals 1. At the top you always have the sub interval from the beginning. Then you have f parentheses bottom of the crowbar plus k times the red width that you got, and then you're going to close your parentheses, and then you're going to multiply it again by the red part that you got from the width. That's all you have to do, but it's very important that you remember this whole idea of it, okay? Like, don't forget that. If that wasn't confusing enough, now we're going to take it a step further. Write a limit using summations that would be equal to crowbar 7, 4, parentheses 4 minus e to the power of x dx. So first you have to find delta x, which is just a thing that shows up on your paper. So you have to just do the width, basically the whole width equation again, except this whole thing right here is the same as the bottom one, except you don't have your sub-intervals anymore, right? See how there's a lack of sub-intervals? But that's basically what n is. So you have 7 minus 4, that gets you 3n. And then you're finding x of k, which is 4, which is your bottom of your crowbar, not the top of the crowbar. I highlighted these two to just emphasize it is the bottom of your crowbar, which is what you're doing. So bottom of your crowbar plus k times your number that you got over here, which is we got 3 over n. So that would get us 4 plus 3k over n. So the formula that you'd have to follow basically, if we're just like plugging it in, kind of, would be limit yada 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 n k equals 1, 4 minus e x of k times delta x, right? So our x of k is 4 plus 3k over n, so it's going to be e to the power of 4 plus 3k over n, and then we're multiplying that by 3 over n, right, which we got from right over here. So now let's look at this a little bit in context. When it comes to the crowbar thing, it is mostly just finding the areas of things, surprisingly. So it's not as bad as it looks, especially when it's given, for example, as it is right here. Let function g be g of x is equal to crowbar x minus 8 f of t d of t. What is the value of g2? So you put in 2 into this thing over here, and you have crowbar 2, negative 8. So you have to find the values from here to here. So let's take a closer look at that. Oh, yikes. I don't know if I wrote it in pencil as well. But every single time you're going up, you have this area, and that's positive area. Right here it's 4. Then you're going down. Whenever you go down, it's always negative. You're always subtracting that part right here. That's 8. Then you're going back up, and that's 20, okay? So from negative 8 to 2, you have 4 minus 8 plus 20, which would get you 16. So that's how you do that. Now, it is very important that I mention this now so you don't get stuck up later as you're working on homeworks or whatever. You may need to flip your crowbar around. For example, if you have a smaller top number than your lower number, for example, like negative 2, 2. So if you were to flip it, you're just flipping the numbers around on your crowbar and adding a negative sign. So that would be, instead, it would be negative crowbar 2 minus 2. Does that make sense? Right there, just like that. So now let's look at derivatives of integrals. So I have f of x is equal to crowbar 3x to the power 4 minus 2, parentheses, t squared plus t over 6 dt. So I have to find f prime of x. So I would find f prime of x by finding the derivative of the top part of the crowbar times inputting that into the original equation, which is t squared plus t to the power of 6. So for this one, that would be 3x to the power of 4 prime, which would be 12x to the power of 3, times 3x to the power of 4 squared plus 3x to the power of 4, which is 9x to the power of 8 plus 3x to the power of 4 to the power of 6. Make sure that you do simplify this, because this number in and of itself isn't really numerical. You don't want to have these primes. However, if I did find this and I had this, that would be numerical. You don't want to simplify too far, because that's when you make mistakes and you start screwing it up. And that's when you start losing points on tests and quizzes and such. Let's look at analyzing intervals. This is very reminiscent of the unit before this one. I think that was unit 5 or unit 6, something like that. G of x is equal to crowbar x1 f of t dt. Determine all intervals on negative 9 to 9 where g is increasing. So, because g of x is equal to the crowbar, which is like the antiderivative, I've been calling it crowbar because it's easier to look at it, but it is basically the antiderivative. So g prime of x would be equal to f of x, right? So if I were to prime this right here, I would get f of x. That's basically what it's saying. Using this logic, though, we can deduce from the knowledge that we gained from, last unit's test that when f of x is positive, that means that g of x is increasing, right? If that makes sense, just as we did before. So all these parts right here, if this was my graph of f of x, this is all where g of x is increasing. So let's take a look at f of x is equal to crowbar x minus 2 g of t d of t, or gt dt, find f of 2. So all you're doing is you're finding the area inside here, right? You're just putting that 2, inputting that into the top part of the crowbar, 2, negative 2. You're finding the area. You will usually get a graph for this kind of equation, or maybe a table, something like that. And you're simply finding some like very geometric simple functions. It shouldn't be too hard. We have 5 and 3, and we have negative 2 to 2, so that's 4. 4 times 2 divided by 2 because it's a triangle, right? We're doing this just as the top part of the triangle. That will get us 4. Then we're going to do our rectangle here at the bottom. So we have 3 to the bottom, which is 3. That's our height. Our width is still 4. So we do 3 times 4, that gets us 12 right over here. So you add those two together, 12 plus 4 is equal to 16. That gets you the area. When you're looking for the answer to the antiderivative or the answer to the crowbar, you are finding the area of what's inside those lines. That's basically all that you're doing. Okay, so this part is a bit difficult, so I'm going to work through it just, by showing how it's done, like together almost. The graph f prime, the derivative of f, is shown on the graph below. If f, negative 6, is equal to negative 4, what is the value of f of 9? So if you're looking for the value of f of 9, you're going to have to use this equation right here. F of x is equal to the y-intercept derivative of x minus y-intercept. So it's going to look something like this, right? So f of x is equal to y plus crowbar x, y, f prime of x dx, just like that. Now, for this one, we're going to do f9, and we're going to put in f negative 6, and now we're just going to start filling in that stuff with the crowbar. So 9, then negative 6, f prime of x dx. So for the negative 6, we can just sub that into being negative 4. But the 9 to negative 6, we're going to have to use this graph on the screen right here. So this triangle is from 2 to 3. So that has an area of 3 because you have to divide it by 2 because it's a triangle. Then you have from 2 to 3 because it's a rectangle, right? So you add 6, right? Because 2 times 3 is 6. Then from 2 to 2 divided by 2 is 2, so you add 2. Then you subtract 1/2. Oh, whoa. You have to subtract right here because this part is all a dip. So you go 1, 2, 3, 4 times 1, 2, 3, 4. You have a 4 by 4 right here. So that's 16 divided by 2 is 8. So you're subtracting 8. And then you're subtracting 1, 2, 3, 4, 1, 2, 3. So you have a 3 by 4, that's 12, divided by 6 is negative 6. So you have your negative 4 from the beginning, and you are adding the area, the sum of these numbers all together to get your f of 9. And that will get you negative 4 plus 11 minus 14, which is equal to negative 18 plus 11, which is negative 7. That's how that one is done. It's not all too bad. Relatively, this should be not all that challenging. It's just important that you memorize all those things to the best of your ability. Good luck.